Right. Good morning. I'm MyungJoo from Samsung, and I'm going to present you about our project, nnstreamer. This nnstreamer is going to support any arbitrary neural networks for GStreamer as yet another media plugins. But it's not like a DeepStream or other neural networks plugins because we are going to support any arbitrary hardware. So we are not going to be depending on any hardware, any specific hardware or software platforms. So let's start. So who am I? Yeah, I'm working in Samsung, and I have been previously working on Linux kernel or another OS, Tizen, and I've started working on a GStreamer project like 5 months ago. So I'm kind of still a beginner in GStreamer community, and all of my teammates are beginners in GStreamer as well. So what is GStreamer? Well, in short sentence, I'm going to say that we are going to let GStreamer handle Tensor. And here Tensor is just simple multi-dimensional array. So it's just another binary data or a simple C array. And why we are going to support Tensor here? It's because Tensor is the input and output of neural networks. So if we can support arbitrary tensor in GStreamer, then it means that we are going to support arbitrary neural networks in GStreamer as well. So nnstreamer is going to give you the set of GStreamer plugins that invokes arbitrary neural network frameworks or models. And it supports such models as stream filters. So each neural network is going to be another element in your GStreamer pipeline. And it also gives you some elements that manipulate stream data. And yeah, neural networks is just another media filter then, and data to neural networks is just another stream data in your GStreamer pipeline. And we already have opened our source code to github.com, and we are developing in github.com, so we are not hiding anything from others for our development. And we want to upstream to GStreamer good plugins. Or we may start with the bad or ugly, but we ultimately are going to upstream to the good plugins. And yeah, we have already released for Tizen, and we are going to support Ubuntu as well. And our CI system is trying to test all the test cases for Tizen and Ubuntu, and then Yocto. And later in next month, we are going to add Android and AR64 for the test cases as well. So our main focus is on embedded systems. So obviously our products are embedded systems, so the first target is embedded systems. And we are not going to abandon the PCs or servers, but that's kind of secondary targets for us. Okay. Background. nnstreamer was not our primary project. It was kind of spin-off from other project. And I'm going to show you what was the original project that required nnstreamer. So I was in the autonomous vehicle team, and we had a lot of sensors in a vehicle. It has like more than 8 cameras, high-definition cameras, and it has more than 4 or 5 lidars, and it has about 10 radars. And it also has other sensors that streams data into our neural networks. And at the same time, it has a lot of neural networks. It needs to detect objects, and then it needs to recognize what kind of object that is, and then it needs to track that object, how fast it is moving, or where it is going to be in next 1 second or 2 seconds. And it needs to segment the images, so where we are going to be in like 10 seconds later. So we need to find out which part is the road, which part is the pedestrian crossings, or which part is about signs. And then we need to find out which is the lanes. So we need to do lane detection. And then we need to find out where we are. So we need SLAM algorithms. And then we need to plan where we are going to be in next hour or next minute. And we need to control the brakes, accelerators, and steerings. Then there are a lot of data streams between those neural networks. So obviously, some of the networks is going to use cameras as their input. And some other neural networks are using the outputs of other neural networks as its own input. So it becomes a bit complex. And those errors in lab shows that the required bandwidth or throughput is quite high. And those cameras are high depth. I think we were using full HD, so the data rate is quite high there. So we had those kind of issues. The high bandwidth itself is the problem. The real timeness is also the problem. We need short latencies because if the latency is like 2 seconds, then it's surely going to hit someone or somebody here. And it requires complex pipeline topology. Well, it looks like that at the same time, at the moment I saw this network in our project, I thought that maybe GStreamer is going to help us. So that's why I started the project of nnstreamer. And it requires synchronization and parallelism, and it requires some short latency, and it needs to control the jitter as well. Yeah. It requires high bandwidth, like this, and complex pipeline. Well, initially, we were using ROS, which is robot operating systems, and it uses socket communication between the nodes here. So it requires memory copy for every transmission, which I don't like it. And also, because it is using ROS, it provides subscription and publication supports. But it supports it is kind of overkill for our requirement because the pipeline here is not that dynamic and it's not that complex. And GStreamer is going to be sufficient for us for this kind of network. And synchronization, well, yeah, because some networks is going to merge data from multiple neural networks or multiple sources. So we need some synchronization mechanism. And this was kind of headache when we were using ROS. Latency and jitter control, yeah, that's kind of obvious because we don't want any accident here. And another project is multimodal interaction, which is to use multiple sensors or multiple input devices for neural networks. And this is about some robots or consumer electronics and mobile devices. So we have multiple sensors like this. We have multiple services because the consumers are requiring them. And we are going to have a lot of neural networks as well. And there are another neural networks for video. And there will be some neural networks that is going to use both audio and video. Then we have a lot of preprocessors, and then we will have a lot of heavy networks between them. It's going to be a headache if we are not going to use any pipelines or GStreamer like that. So, and the data transmission efficiency is going to be matter. And how are we going to support all these different heterogeneous frameworks? Well, it would be ideal if all these data scientists or AI guys are using the same framework, but that doesn't happen because they have their own custom operators and they have different companies for different divisions, and they are going to use their own frameworks. So we cannot enforce to use the same framework, so we need to support all different frameworks. And how do we integrate those preprocessors? And there is another different types of synchronization. So if model C is using the result from model A and B, and they have different rate or frame rate, then how are we going to use the data from them? So model C requires, because model C requires both the results from A and B, so how are we going to accept them? Or if they are placed in serial, then how are we going to do it? So is it okay to let this model A to spit out that fast? So another problem is that we have app developers, like third-party developers, or even we have second-party developers, and they are going to add new neural networks or new services, and we cannot sure that they are not going to add them. So we need to be open to any new pipelines here. And they may have another sensors. Maybe they can be connected with USB cables. So we had such kind of problems, And why we have chosen GStreamer? Because we did not want to reinvent the wheel. Because all these problems have been, maybe it seemed to be solved by GStreamer already, so we chose to use GStreamer. And then GStreamer for intelligence is like real time, and we can support large data. And why we are going to use neural networks in device, not in cloud, is because we need privacy and data protection. And especially in EU countries, the regulation is going to be more stiff than before. So we cannot send any privacy data into the cloud. So we need to process them inside the device. And well, if the input device is video cameras, then we usually cannot send them in real time to cloud and let them process it because the latency is going to be kill the service. And we are going to have new nice chips, the neuromorphic processing units or DSPs or neural process that is going to give us like more than 100 teraops in mobile devices. So we can now, or we can like next year or 2 years later, we are going to use those neural networks in the mobile devices. So why GStreamer? Well, if you were not GStreamer folks, I needed to persuade that you need to use GStreamer, but I don't think I need to persuade that to you. But one significant factor in our team is that in Samsung, we had a lot of GStreamer developers already. So we have a lot of colleagues to ask about how can we use these plugins or how can we add our own plugins in GStreamer. Okay. Yeah. That's the plus view of our team. The neural network seems to be just yet another GStreamer plugin as well. So that was our focus. We are going to perfect the field. The field here is GStreamer. So what GStreamer needed to understand neural networks? Well, first of all, we need some standard data stream standards for neural networks, which we are calling them as Tensor or Tensors. And method to invoke various neural network frameworks such as TensorFlow, GAFEM, or Keras, or whatsoever. And we need to method to convert between traditional data types like video, audio, text into neural network tensors, or the vice versa from tensor to videos. And then we need some additional methods to handle neural data streams. So we need to merge different neural data streams, or we need to split them. Or sometimes we need to change the dimensions, right? Transposing the dimensions. Okay. The system that provides those kind of methods is nnstreamer. And it is licensed in LGPL so that we can someday upstream to GST goods plugins. And we have released the second version this month, like a week ago, and we are developing the next version right now. Yeah, we are going to go to that. Well, what is the benefits for for the traditional developers? For neural network developers, we are providing some easy way to prototype their own application, testing with their neural networks. And for multimedia plugin developers, we are providing some nice or easy way to get those neural networks into your video pipelines. So the concept, how nnstreamer works. The data between the neural networks is tensor. It's just multi-dimensional array. And this is the type of tensor we are using. So it has dimensional data and frame rate and the type of each element. However, this was not sufficient because there were different mechanisms in neural networks. So for example, if there is a neural network that is going to take two cameras, one camera is RGB camera, the usual camera, and the other is IR camera, then how can we use them in a single neural network? And if neural network is going to give us an output as a two separated semantics, like first is the location and size of object, and the other is the types of object and their probability. Well, they cannot be supported by single tensor to neural networks, so we need some container or multiple tensors. And there were three possible implementations for multiple tensors. The first one is just give the multiple streams into a single neural network. Well, that was rejected because it gives us additional synchronization problems because we need to synchronize the two streams in a neural network, which is not going to support them because TensorFlow or Caffe does not think about that. The second implementation was to merge tensors into a tensor. So if for these two streams, we can merge them into one tensor like that, but that is going to waste a lot of memory there. So that was rejected as well. So our implementation is to have a container of tensors. So the format will be like this. It's just memory chunks of multiple tensor into one frame buffer. So that we can support multiple tensors, which is synchronized already before going into a neural network. So yeah, this is the format of tensors. It has number of tensors. It is limited to 16 because GST buffer is limited to 16. And it has frame rate and types and dimensions. And yeah, you can refer to the wiki in our GitHub pages. And this is not yet implemented. We want to save the tensors into a file system, or we want to load those file systems stored tensors into our pipeline, but this is not yet implemented. Okay. So we have multiple categories of filters. The first one is converter, which converts audio, video, or text into tensor, or a tensor into such conventional media types. And then another type is, the second type is filter, which invokes neural networks, Caffe or TensorFlow or TensorFlow Lite. Currently, the current version supports TensorFlow Lite only because TensorFlow Lite is for embedded systems. Because of that, we chose this as our first target. And it also can invoke custom shared objects so that programmers can provide their own C files or loss files as a plugin for our neural networks. And the third type is utility, which contains a lot of utilities like mux, demux, merge, split, aggregate, and there's tensor transform filters that does all the other arithmetic operations to tensors. And then the last type is connector, which connects to out of GStreamer world, such as some sensors that were not supported by GStreamer, such as LiDAR, radar, or any inertial sensors. And we are going to support tensor sync to applications. And because many of neural network or AI projects are still using RobotOS, we need to support RobotOS from GStreamer as well. So that's going to be loss source or loss sync. So for converters, we right now convert all the three main data types of GStreamer, and we also accept binary blob. It works obviously from video XRO to out of tensor. And then decoder is the opposite of converter, which converts tensor to media types. This example shows how to decode the tensor from image recognition or image classifier. It gives us the probability of each class. So here, the probability of laptop is 0.9. So this tensor decoder will give you the text of laptop here. And for next version, we are going to support bounding box or object labeling and all the other types we are going to use soon. And tensor filter, which is going to invoke neural network frameworks. Right now, we are supporting just TensorFlow Lite and custom filters. And this is how to use them. You just need to specify which kind of framework you are going to use. So here, you are saying that you're going to use TensorFlow Lite, and the model file path is a.tflite. Then you will just automatically call that, invoke the TensorFlow Lite, and use that model to use the incoming data to use the TensorFlow. Or if you are going to use your own shared object, you can just say that you are going to use custom framework, and model file is b.so. And here is the example of utility, which is going to change the dimension into the required one. So it depends on the neural network developers. Some neural network developers want to use the channel, RGB channel, into the first dimension of the array. Sometimes they want to use that on the second or another dimension. So we need to provide some way to give them to change the dimensions in the data stream. And the box is going to merge multiple tensors into a single container of other tensors. And demux is the opposite. And merge is, maybe it seems to be similar with box, but it is not going to give you tensors. It is going to give you the single tensor from multiple tensors. So it is like stitching two video inputs, like camera from left-hand side and right-hand side, and it is going to make a panoramic image from those two cameras. This is merge. It's going to give you the single tensor from multiple tensors. Split is the opposite of merge. It will separate those merged image or sound into two different tensors. And aggregator is a bit different. The merge or box is going to they are going to merge spatially, but this is going to merge the tensors in the timely order. So if we have incoming frames from 0 to 7, and if we want to merge them into one tensor from the different frames, then we are going to use a tensor aggregator. Well, if the neural network is LSTM, which is going to use recurrent data from the previous frame, you can implement those kind of networks with tensor aggregator as well. And actually, we didn't think that we are going to need this kind of filter, but in the process of developing another product, I'm going to show you in later slides, we found out that this is kind of be required commonly in many products. And TensorSync is going to give the data to applications. And LostSync is going to send the topic to another lost node. Source is the opposite. Tensor source is going to get the sensor input other than V4, L2 or our sound sources. So we are going to support LiDAR or LiDAR here. Save is to save file. Load is the opposite. So here is a usage example. Well, this is an elderly care product, which is going to detect any fall down in a room or in a facility. And we have already deployed this product into a few elderly care facilities in Korea and in UK as well. And it has a dynamic vision sensor, which is going to show images like that. So if there is no movement there, the image will show nothing, and it shows only movements. And the resolution is low enough so that we can forget about privacy issues. And it also has UWB sensor, which just detects a wide range of IR data. And this device is using RTIC 5, and I think this is quite cheap. It's much less than $100. It has the first version of this product had some CNN neural networks, and it uses different timing data from the sensors. This is how the pipelines or neural network topology looks like. And then this is implemented by GStreamer. Well, the prototypes of this first version was implemented with Python only. They did not know how to use GStreamer, and we just came there and we persuaded them to use GStreamer for their product. So the number of lines of the code has reduced from several thousand to just tens of lines, and the performance has increased a lot. Well, the pre-GStreamer version has been using like 80% of CPU usage. And after using GStreamer with our pipeline, it is reduced to less than 20%. So they decided that they are going to add more services into this device because they have like more than 80% left. And they decide to add more sensors to the device because they have a lot of resources remaining. So they have added new sensors, new neural networks, new services, and they're going to, in the later versions, they're going to add mics so that they can check the event, what is going on in the room, or if there is any security issues, like burglary alarms, things like that. So we have added those kind of neural networks like within a single day or 2 days. So first time they thought that they are going to need like 5 or 6 developers and they are going to need 2 months, but we just came by and we did it for just with one developer. We completed it in 2 days. So it's high performance and it's high productive. Okay. I'm going to show you how it is actually working. All right. This is a simple example of object detection. This is just simple GStreamer application here. Okay. Yeah, it is not detecting there. Right. And these examples are already in our wiki page, so you can just use that, or you can just use GST launch to invoke any. Really? I'm not going to debug here. Okay, so you can just visit our wiki page to see how it works. And these are going to be quite simple examples. All right. Okay, so right. The failed example is this one. It's going to send the upper side pipeline is going to process with the TensorFlow Lite so that it can detect whether this image is laptop or cameras. And then the result text stream is going to go to text overlay. Then it will be mixed with the original image so that you can show the image and its text output. So this is when we are going to show the demonstration, but in actual applications, they are not going to show these images. They just need the text output from the filter. So we can, so these application developers can use GStreamer for their applications. Yeah, and this is the failed example. I'm not sure why it has failed, but yeah. Here you can see that you can invoke TensorFlow right here, and the model file is here. You just need to specify where the model is. And this tensor decoder is going to decode the result from this TensorFlow Lite model, so that if this result is saying that this is a laptop or this is a textbook or something like that. Okay. We have developed our own CI system for this new nnstreamer. We welcome you to contribute to our project, but we require any developer to pass their pull request to pass our CI system. It has anti-regression, and it checks coding stall, and it tests the integration test with some example applications. And the binary package is released via some development deploy system. We are deploying our binaries with the Launchpad BPA, so you can just apt-get our own our nnstreamer. And Tizen is deploying our package with the OBS, and we are going to provide our packages with the OpenSUSE.org so that we can support Fedora, Red Hat, or any other distros with this OBS system in the OpenSUSE. And how to contribute? You can just visit us at github.com page. The development flow is just default github.com flow. So I'm sure you are already familiar with. And what are our issues or work in progress? This is a case that we are going to support soon, but we don't know how or what is going to happen with this. So this in traditional video streams, this is not going to happen a lot, but in neural networks, especially with language processing, this is kind of standard network. So it is supposed to use the output of previous frames. So here you can see that the output goes to T and it goes back to feedback as an input to the filter. And we want to make sure that the timestamp is not corrupted or some become weird. And we want to keep the synchronization working with this kind of actions. And we still don't know how to make a proper timestamp with this case. Well, we already have solution for this one. It's about having mem copy from the output buffer of TensorFlow write, but it is fixed. And high jitter. Well, unlike most video filters in GStreamer, many of the neural networks have a lot of deep variations in their processing time. Sometimes it completes within like 100 milliseconds, sometimes it requires 2 seconds, and it varies a lot. So how are we going to configure frame rate for streams if we are required to give like 10 frames per second for the output? And we don't want to increase the average latencies because some of our usage cases is autonomous vehicle. And because we are still beginners in GStreamer, we still don't have any ideas how to handle this kind of problems. Okay, here's another example. In the first pipeline, we are getting 60 frames per second, and the downside, we have 10 frames per second. And the filters are going to have different rate, but it doesn't matter if we are going to mux them. And then if our neural network is going to use both camera and LiDAR, and how are we going to synchronize them? So how are we going to drop the frames from the faster camera, and how are you going to reuse or use from the LiDAR? Well, this is kind of open problem, and we are still thinking how to solve this one. Or we will appreciate if you can give us any answers or hints on how to solve this problem. And another application we are right now working on is MTCNN and some additional services after MTCNN network. MTCNN is kind of state of art or recent mechanism to detect faces, and it detects faces from camera input, and it detects different sizes of faces. So it does not require you to be close enough or too far. And it has a bit complex network. Well, sometimes people think that the whole network is single neural network model, but if we can divide and use multiple networks inside MTCNN, we can increase the performance because we can parallelize the algorithm here. So by making GStreamer plugin from MTCNN, we could have increased the performance by about 4 times. And we are still working on this, and we are going to add more services here, like gaze tracking or emotion detection. And it is still working on item. And we are going to integrate into different OS as well. Well, right now, it is already integrated into Tizen and Ubuntu. And in the next year, we are going to release for Android, Windows, or other distros. And for features, we are going to support TensorFlow this year. We are going to support loss sync as well, and decode and merge. And in next year, we are going to support CAFE and LSTM, recurrent network support. And we are going to use some SIMD support for our tensor transform. And we have a lot of new features going to happen. And in 2020, we are thinking about using GStreamer for training as well. And right now, we are using GStreamer for inferences, but I think that we might need to use GStreamer for training if the training data is coming from some real-time sensors or from devices out there. Because we have a lot of devices sold worldwide, like I'm not sure, but it's like hundreds of millions of products sold every year. So we may need to use them as a training source. Then we may need to use some efficient stream pipeline. Then maybe GStreamer is the answer for those problems. And we need to support multi-computer or multi-board because the current projects are using single computer. So mobile phones has one computer, and our autonomous vehicle has one computer. But for robotics projects, they are going to use multiple computers. And we want to have single pipeline for the whole system. So we may need to support multi-computers in GStreamer pipeline. Okay, this is kind of ultimate goal for ours as well. We want to use GStreamer in autonomous vehicle, not just for prototypes, but for commercial products as well. Then we need to pass ACLB, D, or ISO 26262 so that we can say that we are avoiding accident by using GStreamer. But I don't know how hard it is going to be. And some people are working on automotive-grade Linux, and the rumor that I'm hearing is that it seems impossible right now. Okay. So, conclusion. Inferencing neural networks on device, not on cloud and workstation, then we recommend you to use nnstreamer. And if you are inferencing neural networks data from real-time stream, then this is recommended as well. If you have multiple neural networks, then the benefit of nnstreamer or GStreamer is going to be significant. If there's just single neural network, then you don't have any synchronization or performance issues. But if you have multiple neural networks, then you are going to have some problems. If you have a high bandwidth stream, then you need to avoid mem copies. Then you may need to think about using GStreamer, and then you will think about using nnstreamer as well. This is a cheat sheet from our wiki page, which is showing what kind of filters or what kind of GST elements we are providing. Here, the blue are the original GStreamer filters, and the other colors are nnstreamer filters. Well, when we had feedback from our application writers, this cheat sheet had helped them a lot. So when you develop application with nnstreamer, you may want to look at this cheat sheet in our wiki page. All right. Thank you for listening. All right. Any questions or comments?
So today you have a filter, I think, for TensorFlow Lite. How would you see perhaps combining this with the DeepStream SDK from NVIDIA or OpenVINO, any kind of the hardware acceleration for neural nets?
So how do we support hardware acceleration? Well, nnstreamer or GStreamer itself is not going to give you hardware acceleration. The backend of each element is going to support hardware acceleration. For example, if you are using TensorFlow Lite for your own neural network model, Then NN API is going to give you the API to go to the backend, which is going to give you hardware acceleration. So if then you will be able to use ARM-CL, which is going to support Neon or GPU acceleration. So it depends on which kind of backend you are using. It is not directly related with nnstreamer or GStreamer.
So it seems like from your Tensor abstraction, you should be able to use several backends like TensorFlow and Caffe. I was wondering if you will be able to combine, like for example, use a TensorFlow for TensorFlow and a Tensor for Caffe, for instance, on the same pipeline.
That is the exact purpose of our project. We are going to mix up different frameworks in a single pipeline.
Right.
All right. Thank you.